So something that's useful for NMR, that's not strictly just for NMR, but is mostly useful in NMR. Sort of a related concept is something called the hydrogen deficiency index. And this is, it's a way to kind of, what is it? If you look at the molecular formula for a molecule, you can kind of use the hydrogen deficiency index, or the HDI, to predict how many rings or double bonds are in the molecule. And so this can be really useful when you do NMR, because a lot of times you'll have the molecular formula from some other technique, like mass spectrometry or elemental analysis, that we're not going to learn about in this course. And then you can use that molecular formula together with the NMR information to kind of narrow things down. And so if we start, we'll just look at propane. So propane has the molecular formula C sub n H2n plus 2, or all alkanes rather. In this case, n is going to be equal to 3, and so we end up with C sub 3, H6 plus 2, so we see that we get C3H8, and if we went through and counted up our hydrogens here, we'd see that that's correct. We have 3 hydrogens on either side, the methyl group and then the methylene group in the middle. And so we would refer to this compound as being saturated. And so you probably heard this word either in our class, or usually you'll hear it with respect to fats. People will talk about saturated or unsaturated fats. They're talking about the number of hydrogens on there. So when a molecule is completely saturated, we're saying that every single carbon is saturated with the maximum number of hydrogens it could have. An unsaturated compound, unsaturated fats, is something that has a double bond in it, or at least one double bond. And so if we look at this, this has molecular formula C sub n H sub 2n. And so if we calculate, based on n equals 3 for the carbons, we see that we get C3H6. And so we can talk about the deficiency in the number of hydrogens here using this scale called the hydrogen deficiency index. And we would say that the HDI here is equal to 1. So 1 degree of unsaturation is 2 hydrogens. So the way this number comes from is if we come back up here and we look here, and sort of this saturated molecule, sort of we always kind of use a saturated molecule as like the comparison point. If we compare it to the molecule that we have here, we see that it's deficient in 2 hydrogens, and so its hydrogen deficiency index number is 2. It's got 1 degree of unsaturation. If we look at a triple bond, so when we talk about deficiency in hydrogen, we're comparing it to, this is sort of our comparison point. We take the parent, the alkane, that's totally saturated, and we just see how many hydrogens that has, and we compare it to whatever we're looking at, and that sort of is just the deficiency index, or the degree of unsaturation, or whatever you want to call it, for that molecule. If we look at the alkyne, this is going to have the molecular formula C3H4, and it's going to have a HDI equal to 2, because now we come back, we look at this, we've got 4 here, and we've still got 8 hydrogens, so we're down 2 sets of 2 hydrogens, so that gives us an HDI equal to 2. And we can kind of just calculate, we can see that this works on, well actually here's another interesting one, so So if we look at propane, cyclopropane rather, it's got a molecular formula of C3H6. I'm just looking at this, so you don't really need these formulas necessarily to do this. You can just count them up on the molecule. What's our HDI there? Not 2. So 2 hydrogens, right? But that gives us a deficiency index of just 1. So 1 degree of unsaturation. if we look at something that's got a ring and an alkene in it. Yeah, so okay, so sorry. Let me lead into that a little bit better. So what we see here is that molecules with a double bond. We look at if we're trying to understand what the HDI tells us. Molecules with a double bond, have 1 degree of unsaturation or a hydrogen deficiency index of 1. If each pi bond that we put in there counts for an additional degree of unsaturation. So you'll notice that here the HDI is equal to 2. So pi bonds decrease the number of hydrogens that you would have in the molecule relative to whatever the fully saturated parent molecule is by 2 hydrogens, or 1 index of deficiency. When we come down here and we look at cyclopropane, we see that we have an HDI equal to 1. Okay, so what we're doing here is what we're trying to see here is how changing the structure of like an organic molecule, in this case propane, how changing it, putting in double bonds or putting in rings, affects the formula that you get for it. And so all we're doing is we're taking if this is the saturated version up here, C3H8, that's the maximum number of hydrogens we can have. And then we're saying, well, what happens if we put in this double bond here? Well, we see that we lose 2 hydrogens. What if we put in another pi bond? So, a triple bond now. We lose another 2 hydrogens. So we can kind of deduce a rule here that pi bonds each count for an HDI equal to 1. That's sort of what we deduced here, right? Every time I add a pi bond into a molecule, I'll see that it'll be 2 hydrogens down from whatever the parent chain would be. Okay, and that's not unique to propane. We're just kind of using that as a molecule to learn on. And so then we come down here and we see what happens if we put it in a ring. So if I make cyclopropane, what do I see happen? Again, I see that I get a hydrogen deficiency index of just 1. So the number of hydrogens on the molecule went down by 2. So rings also count for an HDI equal to 1. Yeah, so how does this work? So practically what ends up happening is, let's see. So I guess what you would what you normally get if you were trying to work this out with NMR or something, since that's the context we're kind of learning it in, you might be given some sort of spectra that looks like this. You've got a bunch of peaks and stuff on it, and all the other information that comes on the NMR, the shift and the integrals and stuff. But then at the top, usually you'll be given something like C3H6. And sometimes there's if you look in the book, they'll usually give you some other hints as far as what's going on there. But C3H6, if you can say what the HDI is there, so the HDI is equal to 1, this helps you hone in on what the potential structure is here. So if you go run down to the NMR and you know your molecular formula, and you've got your spectra and you're trying to figure out what that spectra corresponds to, the place you kind of start at is looking at the hydrogen deficiency index, because this immediately tells you that if I have 3 carbons but only 6 hydrogens, if I look at the parent chain, which is C3H8, I know I'm down 2 hydrogens. What could it possibly be? What could the molecule look like? Well, I know that it has to have a double bond in it, or it has to be a ring, right? That's what the HDI sort of tells me. It sort of narrows down what the different possible species could be. So I could, for example, in this case, I could say, okay, well, I know it's got to either be this or this, because they're the only 2 structures that would work with this, and given the HDI that I have there. And then I could come down here and sort of do the NMR analysis like we talk about in the other videos, where you're saying, okay, well, like what kind of splitting do I expect, for this ring, and how many groups of signals would I expect for each of these things. And, I just made this NMR down here up, so there's no way to really match it. But that's sort of what we're going towards here, and sort of why we're learning about this HDI thing. Okay. So if we look at another molecule like this, we could say, well, what's the HDI of this? We could say, well, it's got 6 carbons. So you want to use the parent chain here to deduce it. What would the fully saturated molecule be? It'd be 6 times 2 plus 2, so H14. And remember, that comes from this formula, which is probably one of the first things we learned in the course that maybe you've forgotten. This gives you whatever the saturated alkane is going to be. And then we look at what we actually have there. So you could just come in and count up the hydrogens. We sort of know already what we're expecting here, right? But let's go ahead and do it anyway. I've got 2 hydrogens there. 4, 6, 8, 10. So what do I actually have for this molecule is C6H10. And then I come back and I compare it to what the saturated alkane would be. So I'm comparing it to this. 1, 2, 3, 4, 5, yeah. I'm comparing it to that. And I'm saying, well, if I look at this and I look at this, I'm down 2 hydrogens. What's my hydrogen deficiency index there? I'm sorry, down 4 hydrogens. What's my hydrogen deficiency index going to be there? It's going to be 2, right? But this is what we would have predicted, because if you come over here and look, it's got a pi bond in it, which we know counts as an HDI of 1 for each pi bond. That's what we learned up here. And then we also see that we're in a ring. And we know that the ring also counts for an HDI equal to 1. And so we would expect those to sum up and get an HDI equal to 2. Okay, so again, this is an example of where we'd use this is you wouldn't be given the structure and asked to calculate the HDI. I mean, maybe on an exam or something just for testing purposes, you might see that. But normally you're just given the molecular formula in the NMR and asked to sort of calculate what it is, and it helps you narrow down what the structures could be. And so if you want to figure out what the HDI is or how different things affect the HDI, all you have to do is just draw any molecule with any functional group in it and compare that to the parent chain to figure things out. So if we look at this molecule, for example, we could say, well, how does having OH in the molecule affect the hydrogen deficiency index? And so we can compare it to the parent. So this is the alkane. And then we can just come down here and look, and we could say, well, we've got 3 of these, 4, 5, 6, 7. So I've got 8 hydrogens. Is that right? 3, 4, 5, 6, 7, 8. Yeah. So what's the effect on the hydrogen deficiency on the HDI by adding an alcohol? Specifically, like if I add this group in, what do I get for the HDI here? Well, the HDI equals 0. So adding in an alcohol doesn't change the HDI by anything. Adding in an oxygen, period, just doesn't change the HDI by anything. I mean, you can do the same thing for chlorine, or like the halogens in general. You could say, well, what effect does this have on it? Well, again, I can take my parent chain and say, okay, I've got C3H8, and then count up what I actually see here. 2, 4, 4 and 3 is 7. So what do I end up with? C3, H7, Cl. So we still want to say our HDI here is going to be equal to 0. And we just want to treat the halogen as a hydrogen. And then we can see here. So what we want to, to make this clear, what we want to count in the hydrogen deficiency index, is we want to count rings, and we want to count pi bonds. Okay, that's what the HDI essentially tells us. It tells us how many rings and how many pi bonds do we have in the molecule. So when you have other functional groups in there, what you're trying to do is come up with a general way to account for those functional groups so it doesn't mess up your count of how many pi bonds and rings you might have. So if you come back to this example here with the chlorine, so if we add in an alcohol or an oxygen at all, it doesn't have any effect on the HDI. It doesn't matter, right? Because it still just works out such that the HDI is still just equal to 0, even by what we had previously figured out. We don't need any kind of new rule. But if you come down here and you add in the halogen, we see that, well, we do come out one hydrogen short. We do come out one hydrogen short here. So if we compare this and this, so it kind of looks like we're missing a hydrogen there, which might imply that maybe you have like half a pi bond, or I don't know how you might think about that, but it screws up our hydrogen count, right? So if you had 2 chlorines in there, let's say I add a second chlorine in. So now I look at how many hydrogens I have. And I've got 6. I've got 2 chlorines on there. So if you were just looking at this, you might be compelled to say, well, normally I have 8 hydrogens, and here I have 6 hydrogens, so I have a degree of unsaturation in there, or I have a HDI equal to 1. That's sort of what the implication would be there. But remember what I just said a little bit earlier is that we want to use the HDI. We want to use the HDI to say how many pi bonds and rings are in there. So really you can think of the halogens as being like kind of interfering. They sort of make it look like the HDI is higher than it actually is. And so we need a way to kind of fix that. And the way to fix that is to, instead of counting the halogens as something separate, we just treat them as hydrogens. Okay, so what's the hydrogen deficiency index in there? Well, you'd count up these. Here you'd say, well, it's 8 to start with, and then I have 6 down here, and then I just count these actually as hydrogens as well, and I see that my HDI is equal to 0. If we look at this nitrogen compound here, this amine, again, we start out with the same parent chain, and then we want to compare it to what we actually have there. So now we see that we have C3H9N. So if you go through and you count up all your hydrogens here on all these different carbons, and the nitrogen, you see that you actually come out with an increase in the number of hydrogens you have there when you add on NH2. And so how do we account for that? Well, what we're trying to do, remember, is just come up with rules to avoid having any kind of conflict. So for every nitrogen that you add in, you want to be sure that you subtract out one hydrogen. So subtract one hydrogen for every nitrogen. And that helps to account for that. So our HDI is still 0. Okay. So you can kind of think of the HDI as, by definition, being the number of or accounting at least for the number of double bonds, and the number of rings inside of a molecule. So all of these other functional groups that I'm adding in that are sort of making it look like I have less or more hydrogens than I should compared to the parent chain, I just need a rule to fix that when I see those present. And that's all we're kind of deducing here. We're saying, well, if I have a nitrogen in the molecule, what do I expect the effect to be on the hydrogen deficiency index? Or what do I expect it to do in terms of like causing noise for the hydrogen deficiency index? And I come over here and I look at this and I say, well, it's going to make it look like it's got one extra hydrogen than it should. So I just make sure I subtract out a hydrogen for every nitrogen I have. And so you can go through and kind of do that for any functional group. If you go online and you go in a textbook, probably our textbook, and look at the hydrogen deficiency index, it will just straight up give you a formula, which of course I'm sure you will not be opposed to using on an exam or something. But you don't need, I have trouble remembering formulas in general, especially weird ones like this. this is one I just pulled from the internet. I'm just going to assume it works. Oh, no, I see. Hold on. Let's see. So if you have a formula here, you would write out sort of a general molecule like this. Right? And then we could apply any formula to it where we say that the hydrogen deficiency index is going to be equal to 1/2 of 1/2 times 2 times whatever the subscript C is, plus 2 minus H minus X plus N, where N is the number of nitrogens. Yeah, you'll notice that even though we have this is sort of what we deduced earlier. So yeah, let's see. So N would be the number of nitrogens that you have there. X would be the number of halogens. H would be the number of hydrogens. C would be your number of carbons. This 2 right here accounts for the 2n plus 2 inside of the original formula. If you play around with this for a little while, you can deduce this formula naturally. But you're basically doing the same thing that we saw earlier. So you can either remember one of these formulas, which I think is, for me at least, it's kind of hard, or you can just like quickly deduce it by looking at like propane's probably the easiest one to look at, and so we can look at using both here. So like let's say you're looking at, let's start by looking just at this molecule. So if I have this molecule and I'm saying, well, what's the HDI for this molecule? If we use the, if you use this, let's say you just look at the molecule. So remember that all we're really concerned about are the number of pi bonds and the number of rings in there. What's going to be the HDI here? Well, the HDI is going to be equal to 1 by just by analysis. If you were to try and do like a count like we did earlier where we say, well, okay, the parent chain is going to be C3H8, and then we count up the number of hydrogens, we'd say there's 2, 4, 6, 8. Okay, so at first glance you might say, well, okay, the molecular formula for this, did I mess that up? 2, yeah, I counted, this would be 2, 3, 4, 5, 6, 7, yeah, so H7, there we go. I accidentally counted this as more than 1 hydrogen. I'll just go ahead and draw them in since I made a mistake. So yeah, 1, 2, 3, 4, 5, 6, 7, yeah. Okay, so we could compare that to the parent chain, which is C3H8, and we'd say, well, this is weird. All right, we'd have like half a hydrogen deficiency index. How's that happening? And you'd say, oh, wait. I know that nitrogen we have to subtract off 1. I'm sorry, for nitrogen we have to add 1 back in. Subtract 1 hydrogen. Nitrogen we have to subtract 1, excuse me. So this goes to C3H6. Okay, that's how we kind of think about it, and that's why we lead to an HDI equal to 1. More in line with kind of how you see this stuff in an exam or something. You wouldn't be given the structure and asked to get the HDI. You'd be given the formula. So if you were to look at, for example, the other way, so forget about the molecule that we drew and just told you were just told this. And asked what's the HDI for this. Okay, so now you can't just go in and count up the double bonds or count up the rings, because that's just usually not how it's presented. It's just, this is just how we're kind of learning about where these things come from. You'd say, well, what's the HDI here? So then you would be kind of forced to go either use this formula or to kind of do what we just did and say, well, I know what I would probably end up doing, because I legit forget these things. I would say, well, there's a nitrogen in there. What's the effect of the nitrogen going to be? Say, well, okay, what happens if I have propane? And I compare those two. I have 3, 4, 5, 6, 7, so that would be C3H7. And down here, I know this is C3H8. So I could see by looking at just this quick example that I came up with that the nitrogen sort of artificially reduces the number of hydrogens by 1. So if I want to compare the number of where did I mess up here? Okay. Derp. I lost a carbon there. I was like, something doesn't make sense. Yeah, what would I see here? I'd say, well, okay, I've got 3, 4, 5, 6, 7, 8, 9. There we go. Now the world makes sense again. So I'd see that the nitrogen sort of artificially inflates the number of hydrogens that I should have there by 1. Right? What's the hydrogen deficiency index of this molecule by inspection? Well, it has no double bonds and it has no cycles in it, so I know that the hydrogen deficiency index should be equal to 0. But what I see when I compare these two things is I see this 9 and this 8. In order for the HDI to be 0, those two things have to make sense together. So I could say, well, okay, for every nitrogen that I see, I have to subtract 1. Subtract 1, that's supposed to say hydrogen. Okay, so for every nitrogen for every nitrogen that's in the molecule, I have to subtract 1 hydrogen out. Since the nitrogen sort of artificially inflates the number of hydrogens that I have there. And so, yeah, so when I come back up here, I would say, well, when I look at this molecule, I'm saying, okay, C3H7N, I know that the nitrogen artificially inflates this, so I would then take the parent chain, which is C3H8, and just compare it to what I sort of practically have here, which would be C3H6 nitrogen. So this is, that 6 is not real, right? But that's sort of what we're using to calculate the hydrogen deficiency index. And I would see that, oh, okay. Now when I take the 2 and subtract them out, I get 8 minus 6 is 2. So my HDI equals 1. If you want to just use the formula because this is too convoluted for you, which I respect, as I'm saying it, I'm like, this is not super clear. What you would do there is just say, okay, you would kind of memorize, although for us, because it's open book, you would kind of just have this out somewhere. And you would say, okay, I'm going to take 0.5, and then I would just kind of fill these in. So how many carbons do I have? So here, let me rewrite this down here too. Yeah, so now I just go in and plug everything in. So I take my original formula, so I don't have to do any kind of thinking here. And I say, okay, like what is C equal? What does C equal? C is equal to 3. And then what does H equal? H is equal to 7. So I'm getting these from here. And then I look at the other ones. What does nitrogen equal? Oops. Nitrogen's equal to 1. And then finally, what do oxygen and the halogens equal? Well, these are just equal to 0 here, so they don't actually have any impact. Yeah, so I got my nitrogen down there. And then I just plug all that in. So 6 plus 2 minus 7 minus 0 plus, what's n? N is actually the number of nitrogen, so plus 1. 6 minus 2. 6 plus 2 is 8, minus 7 is 1, plus 1 is 2. Yeah, so we see that HDI is equal to 0.5 times 2, or that the HDI is just equal to 1. Right, so same answer. So yeah, so we'll look at this. We'll see the HDI pop up again in one of the practice questions that we do for homework. But that's what HDIs work, how HDI works. So again, I'll just to reiterate what you'll see this like. You might see something like in a problem. You might see something like this, and then underneath it you'll have the spectra. So the assumption here is that, like, for whatever reason, you know the molecular formula, some instrumental analysis that you didn't do, but you're given it in the problem. And then down here we have our NMR that looks like whatever, this thing. And you're saying, okay, like, what do I have here? So what you would want to do, the first thing is just say, well, what's my HDI? And so you'd either use this formula or you'd use some other thing that I just taught you, like, recognize that the chlorine just counts as a hydrogen, deduce that somehow. And then you would calculate your HDI to whatever it's supposed to be. What would it be? It seems like it would be something really extreme here. Anyway, and then you would use that to sort of deduce what's going on there. C4, let's see, that should be H10, but it's actually H6. So yeah, so I think your HDI for this would be equal to 2, if I did that right in my head. So your HDI would be 2 for this. I'm trying to think if you can even have a molecule like that. But it reduces the number of possible structures you could have. So you might have something that looks like this if you've got 4 carbons, or you have something that looks like this. There's a bunch of different, there's a handful of different ways that you can kind of make this work. Maybe those are the only 2 ways. And then you'd have to have a chlorine stuck on here somewhere. So you'd be looking for a splitting pattern that's consistent with one of the different constitutional isomers that you could draw of these molecules. Maybe it's over there, you don't really know. I made the NMR up, so there's no way to really answer the question. But basically, the HDI allows you to reduce the number of possible molecules that you could choose from to match it with the NMR. And obviously, when you're, if you imagine that in real life you were to do one of these things, usually when you go in, you have some idea of what you made. But in real life, you were to do something, right? When you go in and you're like, man, did I make my molecule? And this is what's spit out of the instrument, and you have to actually interpret that. You kind of want all the help you can get, right? Because it just looks like a bunch of squiggly lines. Anyway, so yeah, so that's how you use HDIs practically, and we'll see that maybe in one of the example problems that we work for you, at least for the practice for the quiz. So, okay.